Dr. Armando Duarte started his career in Brazil, where he got Bachelor of Science at the University of Pernambuco, and then Master of Science in Engineering Mechanics at Federal University of Santa Catarina. And shortly after, in '91, he moved to Austin, where he worked on his PhD work under the supervision of Professor J. Tinsley Oden. His dissertation was on HP clouds, a cool name, but his feet were very strongly on the ground. The method later was classified as one of partition of unity methods, and he had the luck, the pleasure, the accomplishment of publishing 4 papers, not only with his supervisor, but such big names as Professor Zienkiewicz and Professor Babushka. And I checked those 4 first papers out of his dissertation. As of today, earn over 3,000 citations. Well, I wish everybody could have something on this record. Armando started his career at University of Alberta, but shortly after a year or so, he moved to University of Illinois at Urbana-Champaign, where he spending most of his career, where he went through the ranks of the assistant associate and full professor since 2015. He is the member of practically all relevant professional societies. I want to mention that he serves as the chairman of the Technical Trust Area on Novel Computational Methods in Engineering and Sciences since 2015 in USACM, and he's the fellow of USACM since the last Congress in 2017. His initial work, as I already said, was on partition of unity method, also known as the generalized finite element method. He applied it to many applications involving multi-scale simulations, and more recently, about the last 10 years or so, also began to work on fracture problems, and sponsored mostly by Exxon and Mobil. His recent article on coupled hydromechanical fracture simulations of non-planar 3-dimensional hydraulic fracture propagation, co-author with his student, and published in the International Journal for Numerical and Analytical Methods in Geomechanics, was one of the most downloaded papers on the subject. Ladies and gentlemen, it's my pleasure to introduce to you Professor Armando Duarte.
Well, thank you, Leszek, for your kind introduction. I also want to thank the organizers for the invitation to give this talk. I'm very grateful for the opportunity to share with you some recent developments in the generalized finite element method. I will start with a few slides on one of the applications that has driven our work on GFEM in recent years. The simulation of fracture propagation has been one of the main drivers for the development of GFEM since the early days of the method. And the reason is that this is a challenge problem for the standard finite element method, in particular in multiphysics problems like hydraulic fracturing propagation. So in this slide, we have a horizontal well with 3 stages of hydraulic fracturing treatment. It was showing earlier.
Yeah, I know. It went green for a second. Can we, There we go.
Thank you. All right, so as I was saying, our work on GFEM has being mainly driven by one of the applications which is shown on this slide, which we have a horizontal well with 3 stages of hydraulic fracturing treatment. This stage has been completed, this one is ongoing, and this will be the next stage. So each stage has between 3 and 8 fractures, which are typically spaced between 10 and 30 meters apart. Each fracture starts from a cluster of perforations, as shown in this figure. And this cluster is typically idealized as a radial notch, as shown here. Another common assumption is that fractures propagate on a plane, as shown here. But in reality, this is not realistic. So in reality, fracture interactions and reorientation near a wellbore, like the one illustrated here, cause fractures to propagate and turn away from each other, as shown in this animation. And the consequence of this is that there is a pressure drop near the wellbore, and this pressure drop varies significantly among the different clusters. And so as a result, it has been reported that the majority of production comes from only 20 to 30% of the clusters. So there is still a lot of room for improvement. So it's now well accepted that fracture geometry near wellbore plays a key role on the performance of multi-stage fracturing. However, as we all know, this is a very challenging problem for standard finite element methods. So in the first part of my talk, I will report on some recent advances of a generalized FEM for non-planar 3D fracture propagation. I will also discuss some fundamental issues of the method, such as the control of the conditioning. In the second part, the focus will be on a generalized FEM for multi-scale structural analysis. And I also discuss how to integrate this methodology within existing finite element analysis software. So GFEM can be traced back to numerical methods proposed in the 1990s, in particular the work of Ivo Babuška, Gabriel Kellos, and John Osborne, under the name of spatial finite element method. So many different names were used at that time, but they all share a single concept, which is to use a partition of unit to define approximation spaces. So a very good review paper on these methodologies with also some historical background is this one by Ted Belitsko, Robert Grace, and Julio Ventura. And so as they state in this paper, GFEM and XFEM are basically the same method. So in this presentation, I call the method GFEM, but that also means XFEM. So I'll next summarize the main concepts of the method for those that are not familiar with it. So this equation represents a GFEM approximation of a displacement field U. It's given by a standard finite element approximation augmented by a GFEM enriched approximation. These functions, L sub alpha I, are known as enrichment functions, and their product with a standard finite element shape function give us a GFEM shape function. So this is given in this equation and also illustrated in this figure. So here at the top, we have a standard finite element shape function that is defined on this patch of elements shown here. In the middle, we have a generic enrichment function L, and at the bottom, we have the product of these two functions that gives the GFEM shape function. Now, the key ingredient is the selection of the enrichment functions. So typically, we use a priori knowledge about the solution of the problem to select the enrichment functions. So for example, in a problem with a crack, imagine that now this domain has a crack. Instead of modifying the mesh to fit the crack line, enrichment functions that can mimic the discontinuity of the exact solution along that line are used instead. So in the case of fracture mechanics, in addition to the Heaviside function, we also use polynomial enrichments and crack tip singular enrichments. So this again reflects the a priori information that we have, analytical information that we have about the solution of the problem that we can use to define the approximation spaces. So let's see one example. So in this problem, we have a three-dimensional domain with an inclined crack. the boundary conditions are such that the exact solution is given by the first term of the mode 1 to the asymptotic expansion of the solution. So instead of using a mesh that fits the crack surface, enrichments assigned to these nodes are used to represent the crack discontinuity and the singularity. So we use a quadratic GFEM approximation together with the enrichments that I showed on the previous slide, heaviside and crack tip singular enrichments. So in this figure, we have the deformed configuration, and the color represents von Mises stress. Now, in this plot, we have the convergence of the GFEM solution in the energy norm. And we can see that the method delivers optimal convergence. Remember that we are using quadratic approximation, and this was done on a sequence of uniform meshes. So that's the good news. However, as it's well known, the conditioning, the scale condition number of the GFEM matrices is typically much higher than in the standard finite element method. So in this plot, in the vertical axis, I have the scalar condition number of the GFEM matrices versus a number of elements in the x or y direction. And we see here that the growth rate of the scalar condition number is 6, 3 times the standard finite element method. So the question is how to address this issue while preserving the optimal convergence of the method. Okay? So one strategy that has been proposed by Ivo Babuška and Uday Banerjee is the so-called stable generalized FEM. And this method involves some simple modifications of the enrichments. So given a generic enrichment L, we subtract from it its finite element interpolant. Then the modified enrichment is used as before to define shape functions, multiplied by a finite element partition of unity. So to illustrate this, let's look at this 2D example here at the bottom. On the left, I have the generic enrichment that we saw earlier. Now let's modify it using its finite element interpolant. So this is the finite element interpolant of this function at the top. This interpolant is defined using the finite element mesh itself. So next, we subtract the interpolant from the enrichment to get the modified enrichment. And from that point on, is exactly the same as in GFEM, multiplied by a partition of unit to get the shape functions. Okay, so very efficient from the computational point of view and simple to implement. So let's see how it works. We found that for fraction mechanics problem based on first order approximation, the SGFEM that I just described works pretty well. However, when we try to use this for high order approximation, the method could not control the conditioning or was not giving optimal convergence, one or the other. So we found that for quadratic approximation, for fraction problems, for example, we need to use a discontinuous interpolant to modify the singular discontinuous enrichments. So the equations to modify the enrichments they are given here, but instead of going through them, I think it's easier to explain using a 1D example. So suppose that we have this 1D mesh, and we assign to one of the nodes a discontinuous enrichment, like the one shown here. So to modify this enrichment, we start by multiplying it by a heaviside function. So this leads to a continuous enrichment in the case of the singular enrichments using the GFEM. So that's a property of the singular discontinuous enrichment using the method. When you multiply by a heaviside function, you get a continuous function. So now that this is a continuous function, I'll interpolate it exactly like in the SGFEM, using the finite element mesh. And next, we multiply that continuous interpolant by a heaviside function. And that gives us a discontinuous interpolant of the original enrichment. And finally, we subtract the discontinuous interpolant from the enrichment to get the modified enrichment function. Okay? So a couple more steps compared with the original SGFEM, but now, as you're going to see later, we are going to recover optimal conditioning while preserving the convergence rate of the method. So this is done like in the SGFEM on a node-by-node basis and at a fairly low computational cost. So let's see how it works. This is the same problem we saw earlier. a 3D domain with an inclined surface crack. And here I have the convergence in the energy norm of the solution computed with these two methods, the GFEM that we saw earlier, and the SGFEM with discontinuous interpolant. And we can see that the two curves are on top of each other. And this means that the approximation spaces for these two methods is exactly the same. So we have changed the basis but not changed the space, and we actually proved that. However, the scalar condition number of the stiffness matrices for these two methods is quite different. So here is the same curve that we saw earlier, the behavior of the scalar condition number for GFEM, and this is for the SGFEM with discontinuous interpolant. Now the growth rate is 2, exactly the same as in the finite element method, 3 times less than in the GFEM. So now we have a method that delivers conditioning of the same order as the standard finite element method and optimal convergence rate. The method converged as if there was not a crack in the domain. And again, this was on a sequence of uniform meshes. So if you are interested in more details about this, including applications to fully 3D problems, and also comparison with common practices in fractal mechanics based on the standard finite element method, there will be a talk this afternoon by Alfredo Sanchez Rivadeneira, where he's going to present more details about this SGFEM. So he's presenting this at Mini Symposium 1601 at 3 p.m. today. So now let's move on to the application of the problem to the simulation of hydraulic fracture propagation. So I'll start with the mathematical model that we have adopted. So for the rock deformation, we are adopting 3D elasticity equations. And the reason for that is that we are interested in ultra-low permeability shale reservoirs. And it has been reported that for this type of reservoir, the adjustment of pore pressure due to mechanical deformation in shales is very minimal at the time scale of the hydraulic fracturing treatment. For fracturing fluid flow and pressure, we use Reynolds equation and lubrication theory. Here, W represents the opening of the fracture, and Q the flux, the fluid flux in the fracture cavity. And I want to note the highly nonlinear relation between flux and pressure gradient. For fracture propagation, we adopt linear elastic fracture mechanics. Here, K1 is the mode 1 stress density factor, and K1C the fracture toughness of the rock. And the justification to adopt this model is that the fracture process zone in shale is much smaller than fracture and reservoir size. So for example, in Marcellus shale, the fracture process zone length is less than 3 millimeters. So as a result, the brittleness number of the problem is very high. And finally, for leak-off from the fracture cavity to the reservoir, if any, we use Carter's model, which is classical in this field. Okay, let's see how this works. So this is an experiment that we have used to validate the mathematical model that I just described to you. So in this experiment, fluid is injected in a well bore, shown here in blue. That well bore is connected to a horizontal fracture, and that fracture is initially parallel to the free surface. Q is the flow rate, the pump flow rate. H, the distance between the initial fracture and the free surface. And sigma sub L is the confinement stress, the in situ stress in the reservoir. Now, because of interactions between the fracture front and the free surface, as the fracture propagates, it turns towards the free surface. And the amount of turning is controlled by this ratio shown here, where again K1C is the fracture toughness. In the case that there is no confinement stress, this will be 0, so the ratio is 0. We get the maximum amount of turning. For large values of this ratio, the fracture will propagate and remain planar. So that's the two limiting cases. So here it is an experimental setup that was used by this group. And here we have the material and fluid properties. Here we have the specimen with an initial flaw, which is perhaps too small for you to see, but that initial flaw is connected to a well bore, which in turn is connected to a pump. So now, in this plot, I have the fracture inflow rate. That's very important because we can see that this fracture inflow rate, which represents the flow of fluid entering the fracture, is much higher at the early stages of the propagation than later on. This steady state value here corresponds to the pump rate. Why you have this transient here? That's due to the compressibility of this injection system. It's not rigid. And so there is fluid stored before the fracture propagates. When the fracture initiates, that fluid goes immediately to the fracture cavity. And this is important to take in account because otherwise you cannot match the experimental results. So this is the cylindrical specimen subjected to confinement stress, and due to symmetry, we model only a quarter of the domain and apply symmetry boundary conditions. And here in this figure, it shows the initial notch using the experiment, 1 millimeter in length. Now, we solved the problem for the case in which there is no confinement stress, and as you remember, that's the case that will lead to the maximum fracture turning. So now this animation shows the evolution of the fracture as fluid is pumped in the system. And as expected, the fracture grows and turns towards the free surface. And one thing to highlight is that we get a fairly axisymmetric fracture shape, even though we use a fully 3D solver, which means that we need highly accurate stress density factors along the crack front to get this axisymmetric shape. So this, again, the fracture at the end of the simulation. Now let's look at some more quantitative comparison with experiments. So in this plot, we have the normalized GFM and experimental fracture paths. On the horizontal axis, I have the normalized fracture radius, and the vertical axis, the normalized distance between the fracture front and the free surface. And in this figure, we have the locations where experimental data were collected. This is a picture from the experiment. And these data points are shown here in blue in this figure. And we can see that the experimental, the GFM predicted path matches pretty well with the experimental results. If you are interested in more details on this validation, there will be a presentation later today by Nathan Schauer at MS 605, where he's going to present further comparison between this simulation and the experimental that I just described to you. So now I would like to move to an application example related to my initial slide, the horizontal fracturing treatment. So the goal of this problem is to investigate the effect of the relative position of initial fractures created from a well bore. You want to find out how much the fracture interact for a given distance between them and their relative orientation. So they are created using perforations, as I showed earlier. So that's one design parameter, the relative orientation and distance that the designer can control. So we'd like to find out how much these two parameters affect the geometry of the fractures. So in this figure, we have a horizontal well bore and the two initial fractures that we idealize as these semicircular fracture surfaces. These are the parameters we have adopted, the dimension of the domain, the material properties, and the prescribed fluid pressure. So here, the goal is to study the fracture interaction. So to simplify, we assume that the fluid viscosity is very low, so we prescribe a constant pressure instead of computing as in the previous example. For the confinement stress, we have isotropic in the horizontal direction, and that's the value of the overburden, the vertical in situ stress. So this is the phase angle, which means the relative orientation of these two initial fractures that we have adopted, 60 degrees. Now, in this animation, we are going to see how those two initial fractures propagate as we inject the fluid in their cavities. So you can see that at first, they propagate more or less on their initial planes, but soon after that, they start turning on a quite complex geometry. We can see, for example, that this part of the left fracture propagates towards the other one, but elsewhere, they propagate away from each other. So it's clear that we need a fully 3D model to simulate this kind of behavior. And also, this result shows that GFEM can be used, for example, to find what's the space in between initial fractures and their orientation, such that we minimize the tortuosity of the fractures. We saw earlier that tortuosity has a negative impact on the performance of horizontal well. Hydraulic fractures created from a horizontal well. We would like to minimize that. So that's of interest for the designer to have a tool that can analyze the effect of different parameters on the geometry of the fractures. Okay, so in all the examples that I show so far, as I mentioned, we use a priori information to define our approximation space, analytical a priori information. So this, again, in this example of fracture propagation, where red nodes are enriched with heaviside functions, and the yellow ones are enriched with crack tip singular functions. However, what if we don't have this a priori information available? Or what if we are dealing with a nonlinear problem, a material nonlinear model, or problems with multiple space of interest, that we don't have enough analytical information to define our approximation spaces? So in that case, we need to find a different strategy to define these enrichments. So let me first show an application that has motivated our work in this direction. So in this application, we are required to capture localized 3D thermomechanical fields on representative hypersonic structural components like those shown on this slide. And our major challenge is how to capture the multiple spatial scales of the problem, starting from airframe scale down to subassembly scale, then to the assembly of a panel, for example, down to the scale of a stiffener, panel scheme, all the way down to fractures that may nucleate and propagate around the connections used in this kind of structure. So they use these so-called spot welds that are used to connect a stiffener to a panel scheme. And as we see in this picture, fractures can nucleate and propagate along those spot welds, or they can propagate through the spot weld itself, leading to the failure of the spot weld. So now there is not enough analytical information that we can use to capture this broad range of scale at the scale of this vehicle. So how to handle that? So for this class of problem, the enrichment functions are computed from the solution of auxiliary local problems instead of defining them analytically. And this is based on the observation that most engineering problems, they are solved using multi-step algorithms anyway, like time steps, load steps, and so on. So then the idea is to use now numerical information instead of analytical one, numerical information available at a given simulation step to define the approximation space for the next simulation step. So in this GFEM, the enrichments are produced numerically instead of analytically. They are computed on the fly during the solution of the problem itself. And these, as you see later, allow us to use fairly close meshes while still delivering accurate solutions. So this GFEM with this class of enrichments, which we call global local enrichments, is denoted by GFEM GL in the next slides. So let's see how it works. So I'll use this simple model problem to explain the method. So this is a lap joint where a spot weld, shown here at the center, is used to connect two plates. The left plate is fixed at this edge, and the right plate is subjected to prescribed displacements. We adopt J2 plasticity with linear isotropic hardening, and the properties are listed here. And we solve the problem using 3 load steps. So our goal is to solve the problem using this mesh shown here of hexahedral elements, where the spot weld is way smaller than the element itself. while still delivering a solution with an accuracy comparable to a reference solution computed on this mesh. So let's see how to do that. So here at the top, I have the global problem at a given load step. And here I have a local problem that was defined around the spot weld, which is our region of interest. So the solution of this global problem provides boundary conditions for the local problem. Having that, we can solve that local problem with the method that's the most suitable for the kind of physics that you are interested in capturing at the scale of the local problem. You can use finite elements, generalized Fvm, peridynamics, as Alex Schweitzer has shown, and also phase field finite elements, as more recently John Doble's group has shown. So you can use your favorite method or method that is most suitable, again, for the physics that you are interested at that scale. Having the local solution, we use that to enrich back the global problem at the nodes shown here in red. And this is done by defining Gfm shape function at this scale using the local solution as the enrichment. This is what this equation tells us. Phi sub alpha is a standard finite element shape function at this scale, and U sub L is the solution of the local problem. Okay? Now, before moving to the next load step, we may repeat this cycle, global-local cycle, to account for the fact that the boundary conditions applied to this local problem, they are not exact. So I'll come back to this issue later on. So on this slide, we have the von Mises stress computed from the Gfm solution and a reference direct finite element analysis model. So visually, they compare fairly well. Let's also compare strain energy and the displacement at the right end of the lap joint. Both computed with these two methods. And we can see that the relative difference is about 1%, even though the mesh using these two methods were many orders of magnitude different in terms of element size. Okay, now let's go back to the issue of inexact boundary conditions applied to the local problem. So besides the global-local iterations that I mentioned earlier, the effect of these inexact BCs can also be controlled by, instead of solving the local problem on this domain, which is the one that we used earlier, we solve on a larger domain with a so-called buffer zone. This larger domain is illustrated here in green, and delta is the so-called buffer zone that is how much the local problem is larger than the one that we used earlier. And also, we want to solve on this enlarged one, but still use the local solution in the original subdomain that we used before, okay? If you do that, then we can prove the following a priori estimate. On the left-hand side, here this function is the exact solution of the local problem subject to exact boundary conditions. And this is the approximate solution of the local problem subject to inexact boundary conditions. So there are two sources of approximations here. And this is accounted in this right-hand side. This first term accounts for the discretization error in the local problem, which we can control, for example, through mesh refinement. The second one accounts for the effect of the inexact boundary conditions applied to the local problem. And here we see the size of the buffer zone that we used earlier. So the bigger the buffer zone, the less the effect of the inexact BC. So this is essentially the mathematical expression of the well-known Saint-Venant's principle. So we prove this using Cauchy-Poulos inequality in this reference for those that are interested in the proof. So now I'd like to move to an application that has motivated this work, which is related to representative hypersonic structural components. So here I have a panel with 4 stiffeners, and they are connected to a panel skin using 168 spot welds. These are the dimensions of the domain and the thickness of these different components. I just want to highlight that these are extremely slender components, and as a result, the aspect ratio of the panel skin is larger than 300:1. So the material is a titanium alloy with these properties listed here. And this model is based on this specimen that was actually built and tested at the US Air Force Lab in Dayton, Ohio. So let's consider at first a uniform pressure applied to the pineal skin. This is illustrated with these red vectors represent the load. And in this case, we can take advantage of symmetry boundary conditions and analyze just 1/4 of the domain. So the spot welds are never discretized directly at the global scale. So they are instead represented through the solution of local problems defined around the spot welds. This is one example of them. So these allow us to use fairly coarse mesh. Again, the element size here is typically larger than the spot weld itself. So in contrast, if you are to solve this using a standard finite element method, now you need to have a mesh that is refined around each one of the spot welds. And as a result, in this case, this direct FEA model has about 47 times more degrees of freedom than the GFEM model shown here. So let's see how the GFEM works for this particular problem. So here again, I have the global model that was discretized using hexahedral elements and completely ignoring the spot welds. And here I have highlighted 3 of the spot welds. This first one is represented through the solution of this local problem, which is defined around the first spot weld. We repeat that for the blue spot weld, the orange one, and so on. And we repeat that 44 times. Create one mesh for one spot weld and copy 44 times. And then you can solve this problem completely in parallel. There is absolutely no communication among these local problems as you are solving them. So very efficient from the computational point of view, parallel computation point of view. Then having the local solutions, they are used to enrich back the global model. In this case, we enrich this node shown here in red. And I want to highlight that this methodology allows us to use different element types at different scales. So at the pineal scale, because of the geometry, is more suitable to use, let's say, hexahedral elements. Also have bending behavior, so hexahedrals are better to capture that. However, at the local problem, from the user point of view, using an automatic depth mesh generator is more convenient. So we can do that without any modification to the method at all. Okay, so now on this slide, I have the von Mises stress on the stiffeners and on the pineal skin computed with this generalized FEM with global local enrichments. And we can see that around each one of the spot welds, we have a stress gradient, in particular at those first 2 that are subject to the highest stress field, and most likely they'll fail. And I also want to point out that these are raw stress. There was no smoothing applied to this stress field. We also compare the GFEM solution with one provided by a direct finite element analysis model, including computational cost and scalability of the methods and so on. So the details are in this reference for those that are interested. So now let's move on to a load that is more realistic to hypersonic environment. And that's the case of localized heating. That's one of the critical loads in this type of structure. In fact, thermal loads are more critical than mechanical loads in a hypersonic environment, especially those caused by shock impingement that may lead to this localized heating. So in this simulation, the pineal skin is loaded by both pressure, as before, and a localized time-dependent heat flux. And even though the load is very different from the previous one, which means that the solution will also be very different, at least locally, the global mesh used to solve this load case is exactly the same as the one we used earlier. So the user doesn't have to spend any time updating the global model to account for the change in loads. The only thing that changed are the enrichment functions, which are computed numerically anyway. So the user does not have to get involved with that. So now this figure shows the von Mises stress around some of the spot welds when we apply this type of loading. And we can see again a very strong stress concentration, very sharp stress concentration, even though we are using a fairly coarse mesh at the global scale. So now in this slide, I will show the animation of the von Mises stress, the time evolution of the von Mises stress at the top, and the evolution of the temperature on the panel at the bottom. And we can see that as the panel is heated up, stress concentration develops in that region. Let me play one more time. And another point to highlight is that even after the panel cools down, there is still some stress concentration in this region. Those are the first row of spot welds, which is caused by residual stress. There was some plastic deformation in this kind of application. This is to highlight that the method is not limited to linear problems or anything like that. We are defining approximation space. We are not making any assumption about the mechanics of the problem itself. Okay, so at this point, you may say, well, all this is very interesting, but how am I going to implement this in my legacy finite element code? Well, our strategy is to not implement this in a legacy finite element code, but instead to combine those codes with a modern GFEM solver. And this can be done non-intrusively, means that you don't even need access to the source code of the legacy finite element code. This can be done non-intrusively using an iterative algorithm called iterative global local that has been pioneered and developed significantly by the group of Olivier Alix. And in this framework, we can have a structural model defining a legacy finite element code using shell elements, beams, and so on. That's what they use at the Air Force and Lockheed. And so now they may be interested in some localized region, some critical region that the shell model cannot capture. So the regions where I have connections like spot welds, around which we have a fully 3D field that the shell, of course, cannot capture. So then the idea is to combine that model with another one defined in another solver, a GFEM solver that implements the GFEM with global local enrichments that I just described to you. Since we can use a fairly coarse 3D mesh, combining these two models through the iterative global local is very straightforward. Okay, so I don't have the time to go into the details, but there will be a whole section of a mini symposium starting at 10 o'clock this morning describing this method with applications to many interesting problems. And I see Leszek raising his hand, so I'm going to finalize with some conclusions and provide one assessment of generalized FEM. In my opinion, the main attractive feature of this method is the flexibility of the method. We can use analytical information, we can use numerical information to define the approximation spaces. And that allows us to solve problems that are fairly difficult or perhaps not practical with standard finite element methods. So for example, the propagation and interaction between 3D fractures, like hydraulic fractures propagating and interacting from a wellbore, as we saw earlier. Another challenging problem that this method can handle is the coalescence of 3D fractures, also relevant for hydraulic fraction applications. So in this figure, we have two fractures just prior to their coalescence, which is shown here on the right. And now if you are to solve this problem using a standard finite element method, you have to create a mesh that fits both of these crack fronts. And creating such a mesh when these two fronts are at close proximity, while still satisfying the requirements of a standard finite element mesh in terms of element quality, aspect ratio, and so on, will be very difficult. Perhaps you can do, but will be not robust to automate, in my opinion. Regarding problems with multiple spatial scales of interest, we saw that GFEM leads to a method in which the fine-scale computations are naturally parallelizable. And also, this method allows us to combine different discretizations at different scales without introducing any additional field in your variational principle. You don't need to add Lagrange multipliers or Morta elements, for example, to glue vastly different discretizations. And in addition to that, this method allows us to combine also different mathematical models at different scales. This was shown by Alex Schweizer's group from Bonn University in Germany, where he used a peridynamics model to simulate fractal branching. This is shown here at the left. Then the peridynamic solution was used as an enrichment function for a global finite element mesh in the same framework that I described to you earlier, but now using a different mathematical model, a different discretization at a different scale. So I believe that the use of GFEM to combine different discretization methods and mathematical models still offer many opportunities that have not been fully explored. There is a lot of, I think, work ongoing, but I think there are still lots of opportunities. In terms of robustness of the method, there has been significant progress in past few years. I mentioned the stable GFEM. There is also the idea of orthogonalized enrichments. Many preconditions for the method has been proposed. And finally, the long-term success of the method, and in fact of any numerical method, requires that we continue to transition the method to the industry and national laboratories. And one pragmatic way to do that, in my opinion, is to rely on non-intrusive algorithms to combine a generalized FEM code that can add capabilities to an existing legacy code without having to modify the legacy code, but augmenting that code with capability that it does not have. And to conclude, I would like to acknowledge the contributions from my current and former students and postdocs. Many of them are presenting their work in this conference. I would also like to express my appreciation for the support from the sponsors of this work. And with that, I thank you for your attention. I will be glad to take questions.
A conventional approach for handling stress concentrations or fracture might be to have what's usually called a breakout model, where you have a fine local model that gets loads from the coarse model. What's the difference between that approach and your non-intrusive approach to take GFEM as the local model and connect it non-intrusively to a coarse model?
Very good question. And this method that you describe is also known as in the industry as a global local model or sub-modeling. And the way it works is, as you describe, you solve a global problem and use that to apply boundary conditions for a sub-model. And that's the end of the story. But if you do that, there is no feedback from the local problem at the global scale. By using the local solution as an enrichment, not as the final solution, now I have a feedback between the two scales and I can account for the scale interaction. The non-intrusive algorithm is just a way of implementing this method using two solvers. The solution will be exactly the same as if I do everything in the same code.
In addition to this question, if we consider super elements, where they condense the internal degrees of freedom, and then you have a feedback to the global solution. What is?
Well, super element is essentially like a static condensation. I see that more as a solution technique itself. And there is some similarity, but now you have to handle everything on the global scale, and you have to change your super elements, depends on what is the load for the structure, for example. Like in the example I show, I have a constant pressure, then I add a localized heating without having to change my global model. So I think here we have more flexibility, but super element in some applications may be sufficient.
Thank you very much, and thank you for the fantastic lecture.
Thank you, Leszek.